Welcome back. This is where routing really starts to get interesting. In Lesson 32, we're tackling redistribution and route maps, the mechanisms that let different routing protocols talk to each other, and the filters that keep that conversation under control. By the end, you'll understand how to share routes between protocols like OSPF and BGP safely, and how to shape exactly which routes cross that boundary. Here's the path we'll take. First, we'll look at why redistribution exists in the first place, what problem it solves when two protocols need to share information. Then, we'll get into the actual syntax, including seed metrics, which is where a lot of people stumble early on. From there, we'll move into route maps and their match and set logic, and finally, wrap up with prefix lists, ACLs, and the filtering tools that give you precise control over what crosses between protocols. So, why does redistribution exist at all? Picture a router sitting between two routing domains, say OSPF on the inside and BGP facing your ISP. That router becomes an ASBR, and its job is to take routes learned in one protocol and announce them into the other. You'll see this everywhere. Enterprises pushing internal routes out to BGP, mergers bolting an EIGRP network onto an OSPF1, data center fabrics running IBGP over an OSPF underlay, or even just making static routes visible to your OSPF neighbors. Anywhere two protocols need to share reachability, redistribution is the bridge. Now, let's see what that bridge actually looks like in configuration. The key thing to notice is that redistribute lives under the destination protocol. So, if you're pulling BGP routes into OSPF, you configure it under router OSPF. Read the command right to left. We're taking routes from BGP 65000 and injecting them into OSPF, assigning them a seed metric of 100, and using subnets, so OSPF carries the classless prefixes properly. And remember, this is strictly one way. If you need routes flowing both directions, you configure redistribution on both sides. That seed metric I just mentioned isn't optional, and here's why. Every protocol measures cost differently, so when routes cross the boundary, they arrive without a value the new protocol understands. OSPF defaults to 20 as a Type 2 external, which is forgiving, but RIP and EIGRP are brutal. No metric means infinity, and your routes get silently dropped. That's probably the single most common redistribution bug. You configure everything correctly, nothing shows up, and it's because RIP or EIGRP threw the routes away. Always set a metric, and for OSPF, don't forget subnets. So, how do we actually control what gets redistributed? That's where route maps come in. Think of them as if-then logic for routes. Each entry has a sequence number, a match condition, and a permit or deny action, with optional set statements to modify attributes like metric or local preference. Evaluation is top-down. Sequence 10 checks first, and the moment a route matches, processing stops. Anything that falls through every entry is denied by default, which is why best practice is ending with an explicit permit or an explicit deny, so behavior is never ambiguous. Let's see this in action. The goal is to redistribute OSPF routes into BGP, but only two specific prefixes, and tag them with a community as they cross over. First, we define a prefix list called allowPublic that permits exactly those subnets. Then the route map matches against that prefix list, sets community 65100, and bumps local preference to 200, followed by an explicit deny 20 to drop everything else. Finally, we apply it on the redistribute statement under BGP. The verification confirms it. Only those two prefixes appear, each carrying the community tag we attached. Now that you've seen a route map in action, let's widen the lens and look at the full toolkit. Every route map is built from two halves: match clauses on the left, which identify routes by address, prefix list, AS path, community, metric, or tag, and set clauses on the right, which modify those routes by changing the metric, local preference, prepending AS path, attaching a community, rewriting the next hop, and so on. Think of it as, if the route looks like this, then change it to that. And almost any redistribution policy you'll ever write is just some combination of these building blocks. One of those building blocks deserves special attention: how you actually identify the prefixes you want to match. You'll see both ACLs and prefix lists used for this, but they're not equal. ACLs were built for packet filtering with wildcard masks, while prefix lists were purpose-built for route matching using clean sitter notation. The real superpower is the Li and GI keywords saying 10.0.0.0.08 Jilla 16 LC 20 matches any prefix within that block whose mask falls between 16 and 24. That kind of range control is simply impossible with an ACL, which is why prefix lists should be your default, always. With prefix lists in your toolkit, let's look at where route maps actually earn their keep in production. You'll use them to stop internal Howard 24s from leaking into BGP by permitting only your aggregate, or to steer traffic by bumping local pref on a preferred ISP. Path prepending makes a route look artificially longer, so neighbors choose the other path, while communities act as tags that downstream policies can act on. And on the OSPF side, choosing metric type 1 versus 2 decides whether external cost reflects the full path or stays fixed, small knobs, big operational impact. Powerful as those tools are, redistribution itself is where engineers most often get burned. The classics, a route loops from OSPF into BGP and back with a worse metric, or you forget the subnet's keyword and watch every 24 quietly disappear. RIP and EIGRP will silently drop routes if you don't set a seed metric. Two-way redistribution without tag-based filtering will eat both routing tables alive, and AD mismatches can send traffic the long way around. The fix in every case is the same pattern: tag on injection, filter on return, and control your metrics deliberately. So let's pull the whole lesson together into 5 points worth remembering. Redistribution injects routes from one protocol's RIB into another, one direction at a time. And because every protocol measures cost differently, a seed metric isn't optional. It's the difference between working routes and silent failure. Route maps give you if-then control: match to identify, set to modify, sequence numbers to order the logic. Pair them with prefix lists rather than ACLs for cleaner filtering, and never run two-way redistribution without tags and filters. That's how you keep loops out of your network. And here's your reference card to keep handy when you're actually configuring this. Remember the essentials. Redistribution lives under the destination protocol. OSPF needs the subnet's keyword for anything classless, and RIP or EIGRP demand an explicit metric or the routes simply won't appear. Route maps follow the permit or deny sequence pattern with match and set clauses, and prefix lists use that LE and GE syntax for flexible range matching. Screenshot this one, it'll save you in the lab. That wraps up lesson 32, but the journey isn't over yet. Up next is the stage 4 capstone, where you'll put everything from this stage together, pulling OSPF, BGP, redistribution, and route maps into a single integration and design ticket that mirrors what you'd actually face on the job. Practice what we covered today, and I'll see you in lesson 33.